So let's take a moment to look at some things with 5 sides. So this is a papaya. We could look at hibiscus flower or jamaica. So there's 5 around, but also on the center where the pollen is. You might look at this and say, well, this kind of spirals around and it's interesting, but where's the 5? And if you zoom into where those little red things are coming out of, there's 5 sides. This beautiful thing is the flower from a passion fruit. I was walking in the park and saw it and had no idea what it was. So even though we see lots of different kind of like sunshine rays coming out and numbers of sides of what we might call a star, when I look at this I think of a star. On the very inside with green you have the 5-sided star. And oftentimes the one with 3 is actually more evenly spaced out. Here we have a cactus. This is a blackberry blossom. It's going to turn into blackberries. This is an orange blossom, and grapefruit and others have 5 sides. This is a plumeria. So they start in a spiral and they spiral open into 5 sides. And some other flowers I've seen on my walks. So you might look at this one and say, well, this has many sides. I think I counted 20. And we could do that. We could make 20. It would just be 5 sides times 4. But when we zoom in and look at the little yellow things that have pollen on them, they're actually 5-sided stars. So we mentioned the Fibonacci number. You may have learned it's in nature and in the galaxy, in the universe, and a shell. And it's a pattern that you get by adding the 2 before it. So like 0 plus 1 is 1, 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3 is 8. And when we draw that, making squares, 1 by 1, 2 by 2, 3 by 3, 5 by 5 squares, when we draw quarters of a circle, arcs, it'll always make perfect spiraling shape. We can represent that in a conch shell. So that number, when we divide the 8 divided by 5, we get about 1.6. And the further we go, we get this number ratio called phi, 1.61. And so the number of the spiral is actually in the 5-sided star. We could look at that. This is actually the Hebrew symbol for God. It's their word or symbol for the God. Really, there's a way to say it. It's kind of like Yahweh, but they don't actually know the way they would pronounce it. And so the word tetragrammaton is a symbol, symbolizes or means to them both this 5-sided star, which to me contains a lot of the properties of growing life, but it also represents the creator, the God of theirs, that they only would name at certain times in the temple, so they wouldn't use the word, the actual name or pronunciation, except certain times within the temple. So most Hebrews don't use the word that I'm referring to. We also know this to be a symbol for something that Plato described as all things are made of these. These are what we call the Platonic solids, and he would arrange them in 5 sides like this, or sometimes he would put 6, the 6th one being a circle or the creator, to go along with the earth, air, wind, and fire, and ether. And of course, when you have the star representing life, and it contains the Fibonacci and phi numbers, when you turn that upside down, it's kind of representing turning life upside down. And that was what we would call the pagan or demonic symbol or devil worshipping symbol. Sometimes they would draw a goat in it. They say they once worshipped someone, I think Baal in the Bible, B-A-A-L, that was worshipping a goat or a calf. So, why is this number so prevalent and used as far back as 4000 BC? I heard or read that it was used. We use it on the sheriff's badge. We use it on, the general stars when they get promoted. And again, we see it all over in nature. And so let's take a quick look at how we make the pentagram. Pentagons and pentagrams, those are shapes with 5 sides that are equal or congruent. And what's interesting, I didn't know this until really recently, that the pentagon, even though it's a geometric shape with 5 sides, it contains in it the math of the golden ratio or the golden spiral, the Fibonacci spiral they call it. So one thing to know is, when I look at these geometric shapes, even a pentagon, I think of connecting the center to each edge, and it looks to me like a star. So stars represent life, and of course, flowers, when you look down on them, even trees, they really look like stars. Maybe that's why they also represent life and other things, like a red rose represents love, and a yellow might represent friendship. So colors also have meaning behind them. But when we look at number 2, they have the number phi in them, or the golden ratio. So you can watch a video on that, but the way we make the golden spiral, we'll quickly look at it. But even though we don't see the actual spiral, a lot of these vegetables and fruits that I see growing, they contain that spiral in their leaves, but then in the flower they contain other geometric shapes. And one thing to point out, we'll look at how to make the pentagon, but they are actually more complex than making something with 4 sides or 6 sides or 8 sides. And if we want, we could quickly look at how to make the other, let's say 4 or 6 or 8 sides. 8 would just be doubling the amount of 4. So we could look at 4 or 6 and see how 5 is a little bit more complicated, as well as the other shapes. So if I take 2, right, now I can draw a straight line and perpendicular lines. And if I draw 3 circles that are the same size, interlocking and touching each other, I can now make a triangular shape. Do another one. Now I can do 4 sides. So I have the ability to make 4 even sides here. So you can see making 4 is very easy. I could actually continue all the way around the middle circle. It would make 6. So making 6 is also easy. We would call that the seed of life. In it you could make a square, a rectangle, a pentagram, not a pentagram, a square. Let me show you. You can draw lots of different shapes from this. So of course we could draw a triangle or the Star of David if we did both, which would also allow us to make a hexagram. We could draw a rectangle here. We can draw, in fact, if we were going to draw a rectangle and stopped here where the 2 intersect, it would make a square. We can draw a diamond or a rhombus. We can draw a trapezoid. So there are lots of shapes within 6 that you can create using a compass and using circles. So let's talk about how we would make 7-sided shape, or a pentagon. It's actually a little bit more complicated. Even making 8 is easier than making 5, because as we just showed, you could make 4 sides pretty easily. And then if we just cut these in half, right, we can add another set of them and cut it to make 8. So it's easy to multiply things. If you have 3, you could double it, make 6. If you had 6, double it, make 12. But what about the pentagram? So the pentagram takes a little bit of extra mathematics behind making it, because the proportions, again, they have the golden ratio in it. I'm using Geogebra, the software, and we're going to show first the final product of a pentagon, and we'll look at the ratio of the golden ratio phi, as well as in a pentagram. But I think first I want to talk about the finished product, then I'll go back and show how to use Geogebra, the software, geogebra.org, to make the pentagon. In the description below, you'll also see a video for how to make a pentagon using a compass. So let's talk about the finished product and the pentagon and some of the mathematical properties behind it. So I'll just take F to each corner, take K, go to each corner, do the same thing for each of them. So now I have the 5-sided star. And right, if we really wanted to, we could do the same thing in here. We have really the ability to make 5-sided star inside of a 5-sided star inside of a 5-sided star. So what's special about this, and where do you see phi, or the golden ratio, which is 1.618? So we see it in a couple of places. The longest lengths, for example, H to K, or from I to K, right? That longest length divided by this one will give us phi, give us the golden ratio, 1.61. We see it again here. This amount divided by the one below it, this amount, also gives 1.61. But since the one below that is also the same as the red one above it, oops, right, oops, this keeps going. I want it to be red. This red piece divided by the black piece on top, or the red piece on top divided by the black piece here, are also going to give you the number phi. So even though you don't see the golden spiral, you actually have the mathematics behind the golden spiral in the shape of the pentagram. So the pentagram is interesting to me, or it's interesting to see in nature, because again, as we see from the construction, there's a couple extra steps to making it as far as when we use circles. So, you know, it makes me wonder if plants that have this shape are a little bit more complex or complicated. I tend to wonder if the ones that have the many different, like 20 sides or 24 sides, or the odd ones like 13 sides, just seem extra special to me as far as mathematically, because they're a lot harder to make in the way that we would make them with circles or with our compass. So that's a little bit about the pentagram or pentagon, and how the number 5 or the golden ratio is built in, and how we see it all over the place in nature and the fruits and the things that we enjoy. Hopefully that opens your mind a bit to some of the things you see around you every day. Pentagram. We're going to start with a circle, and after we do that, we want to go through the center. So we're going to draw what we would call the diameter. Then we're going to find the perpendicular bisector, or cut that in 90 degrees. Oops. So I'm going to get from C to D and cut it in. So now I have half of that original line, the diameter, and now I have 4 equal sides, and that's how we would make a 4-sided shape. So we're going to find the middle of A to D. We're going to find the midpoint. So let me take my midpoint button. From A to D is that amount. So what we're going to do is we're going to use this line I'm drawing, E to F, and we're going to see how far that is. So if I use a circle, I can see EF is my radius, so that same distance goes all the way around, which gives us this point here. So what we're doing here, let's talk about mathematically what we have. Since we have the midpoint of our radius, we can call that 1, and the radius would be twice as big as that. So if we did our Pythagorean theorem, we get the square root of 5. So this line from E to F is the radical 5, square root of 5. So we're going to actually take this amount here, and what we're doing is we're laying out that same amount here. Okay, but we have to consider we're adding to it an extra half. And that's actually going to be then the square root of 5 plus that 1 here. But really what we took was the radius. So I said it was 1, but it was really half. So at the very end I'll get half, which is a terrible way of showing the math. But the square root of 5 plus 1 over 2 is the number 5. So how are we going to use this? Well, what I'm going to do is I'm going to take a line segment G to F, and I'll turn it a different color. So this gives us the amount we need to go around 5 equal times. So what I'm going to do is I'm going to make a line the same length. So I'll click here. Oops. And it'll say, make me a line, how long? Well, I want it to be as long as the one I just said, FG. So I'm going to make sure I put in FG. And now that line is going to be one of the 5 that go all the way around evenly. So I'm going to do that same thing 5 times around. I'm going to click H and say make it as big as F to G. So we're continuing to use that red line. So the first 3 constructions were helping us define the length we need that help us to go all the way around. So again, all the way around I'm just using that red line FG. And if I really am careful, I would zoom in and make sure my points are exactly on, but for the sake of time, I'm going to speed it up a little bit and not do that. So again, F to G, we just need to then reposition it. And then our last one will make a perfect pentagram. And so I really don't need to do that, I can just connect the dots. So now I have a pentagram. So let's erase or hide the things we're not using anymore.